good evening. Thank you for joining me for the solution to this, as you title it, basic integral problem on the height of the influenza outbreak. So, taking from the opening paragraph there, the way that I was instructed and taught in school by my college professor was to list out any and all of the givens that I've got. List what I'm targeting for, what I need to find, and then go at a solution. No cheating yet. You're not allowed to see the solution yet. I'll be sliding into that here soon. So first we know that the rate at the number of cases was approximated by that equation, which the I prime of t is the same thing as saying di dt. The incremental change of I, the number of cases of infection over the little bit of change in time. So it's technically derivatives are ratios of little tiny infinitesimal changes. So we'll be using that to our advantage in the solution, but stating it outright is good to have. And it equals that equation that was stated, the minus 6.34t. So it is a variable rate throughout time. As time progresses on, there's going to be changes in that, plus a little constant part of change. And at the beginning of the estimate, it was stated that there was, at time 0, there were about 1,428 infected people. And then for any time t, what's the solution? So we start off with stating some parts. There's an arrow here because Wyzant doesn't like scrolling down to the end of the page, so I'll be moving to the right. And like I said, that it's technically a ratio of little incremental changes, so we can quote unquote, I believe it's termed abusing notation, and taking it as an actual scalar thing that we can multiply both sides on. Because if we do so, dt over dt is 1. So it cancels out and you get di equals all the things that we had for our for that di dt multiplied now by a dt factor, because here we multiplied the left by dt. Whatever we do to the left, we have to do to the right side of the equal sign. Moving over, because I gotta switch between pencil and mouse. We can now take the integral of both sides. Now, since everything is of dependence on t, whenever we do the regular integral over t, it goes from 0 to t. Whenever you do the integral over I, though, it does a little bit of a different thing. It does the integral from one state of the infected people to another state of infected people. But it should have a one-to-one type of like dependence between the bottom bound on the t integral. So you can state that as the infected people at time 0 to the infected people at time t, because that is boundaries of a di integral. We're telling about the infected people at one point in time versus another point in time, even though we're talking about infected people. So that's just keeping everything legal so we don't cause any issues later along the line. So integral di just goes to, I guess I could have stated that outright. It would be I bounded from I of 0 to I of t, which just turns into a difference of i's there. I decided to not fully solve the right side, to expand a little bit in case the intermediate parts were needed to be seen. So I split that up. Any constant terms can come out of the integral and scale that integral so that it looks more familiar to ones that have been dealt with before. For t dt, you technically can integrate as it is, but it's not a nice one because it would technically go to a power 2, But to be able to get back after anti-deriving it and taking the derivative of that, how do we get it back to just that t form? Well, you can do what's called multiply by 1. So multiply by a 2 there and divide by 2 on the outside. So that has an effect of multiplying by 1. So it doesn't really change it, but it makes the appearance inside here look a little nicer. So in doing that, and the regular, if that's dt, that's going to do exactly what I was stating for the di integral that I didn't fully show out that I probably could have. But anyway, now we have the I of t minus I of 0. And I already showed here that I'm going to be adding I 0 to both sides, but imagine I didn't. Wave magical hands. 6.34 divided by 2 goes to 3.17, still carrying that negative sign, never canceled it. And the t squared, we evaluate that going from 0 up to t, which 0 squared is 0, so it's not going to affect the subtraction there on that one. So we'd get minus 3.17 t squared, parabolic curve. 142.3. I should have had a t there. That should be 142.3 times t from 0 to t, which, again, it's a t minus 0, so just t. And then the I of 0 was stated in the givens of 1428, giving a final answer. At any time t, based on that approximation, the number of infected people is represented by that equation at any time t. Thank you. If you have any questions, comments, or concerns, please put them in the message chain under this solution, and I hope this helps. Have a good night.